speaker in this non-hydrostatic session before lunch, Jinglang Li from the China Meteorological Administration, discussing another non-hydrostatic model.
Oh, thank you. Yes, my topic is about the multi-moment constraint finite model method for non-hydrostatic as mathematical dynamic course. Sorry. Yes, here's our content will be talked. First, I give a brief introduction, and then I give the multi-moment constraint formulations, and here includes third order and fourth order formulations. And after that, I give some benchmark tests. Finally, I give some summary and future works. Yes, now local high-order spectral convection method is very appealing since it's very accuracy and conservative. At the same time, it's highly scalable on the massive parallel systems. Such methods include discontinuous calculus. Here is some present work and spectral element. Yes, recently we developed a kind of local high order method we call it multi-moment constraint collocation method. So, what is multi-moment constraint finite model method? Yes, let's look at this. Start from the conservation law. We defined the moment that is lie integrate average value. This is our single cell, and the point value defined like here, solution point, and the derivative values here is. So, what's done by multi-moment constraint? Yes, you just look for the solution point and the constraint point relationship. This is done, multi-moment constraint done. So how to do? Yes, let's look at this cell element. Here we define the solution point here on blue one, and some constraint point in here. So how to connect it? Yes, we use the Lagrange interpolated polynomial is based functions. So use these interpolation functions. We can connect the solution point we also call DOF, we mean degree of freedom between the constraint. His M is a matrix. And next, I will give detail how to derive this relationship. Yes, here I want to say is, in fact, our solution point is very flexible, not limited to Gauss point or Gauss-Lobato point. In this study, I just use equidistant point. Yes, in our opinions, the solution point is play less sensitive roles in our multi-moment, but constraint condition is very important. Yes, before next I will give some this governing equations. This is the hyperbolic sometimes hyperbolic forms. This is our forecasting variables, the conservative state variables. Yes, when incorporation topography, here we use a high base telephone hybrid called this is the Scout in 2002. Okay, now let's begin the third order multi-moment constraint finite volume. This is one our cell element here. In this cell, we define solution point. For fourth order is 9 point solution point. And at the same time, if we look at the line segment here is line segment. We define the solution point 1, 2, 3 is equidistant point. So how to impose constraint condition? Yes, this first we impose the line intergravity moment over this line segment, which cast in final volume formation. You can get these equations. At the same time, we use another two constraint condition is on the boundary. That one, you can get the evolution equations. So because we have 3 points, so we have to have 3 equations. 3 equations we can 1, 2, 3. We solve this linear system. We can get the solution evolution equation our DOFs like this. Here is our DOF, that is solution point, and here is the flux on boundary and the flux derivative on boundary. So we can use this is our one-dimension semi-discrete equation to update the unknowns. Yes, we can make some notation we can write here. In fact, yes, just we are showing just one in along the x direction. In fact, the same as the z directions. So, using the similar derivations, we can get the 2 dimensions formulations here. Here is our solution point evolute, and this is matrix. This is substance. I want to emphasize that here substance in fact is just a point-wise solid, so no include some numerical quadratures. This is very benefit. Okay, for first order, the same as third order, but we include 1 point solution point. 1, 2, 3, 4. At the same time, 4 equidistant point. Yes, the constraint condition, these 3 conditions the same as MC3, but we add an actual constraint conditions on here, on the segment center. Yes, like this. We forecast the derivative of DOF at the center. So this we can get the second order derivative flux on the center. So how to compute this? Yeah, yes, we use the first order approximations. This formulation. In this formulation, we just the flux on the boundary and the flux at the center. We just obtain formula Lagrange interpolative functions. Yes, this is the full first order semi-discrete formulation for first order. This is matrix, and this is the flux. By now, we assume the flux and flux deductivity is known. Later, I will give you how to compute this flux and on boundary. Yes, this is because we defined the solution point on the boundary, so it is continuous on the boundary. So for numeric flux on the boundary, we can deductively calculate from the values and state variable at the boundary solution. But for flux derivative on boundary, we use derivative driven problem. This followed in 2001 and 2002. So this computation we can get the flux derivative. Yes, so all of them we have compute get the values on the boundary. So it's over for our MC scheme. Everything is known. Yes, this just gives some numeric formulation for, because in late our test have to use the dynamic or quantities like that. This formulation deduct from our interpolation polynomial. And boundary, yeah, that's the no flux boundary used when we on the bottom of a model. Is we just copy, for example, for set order, copy symmetrically. But for normal monodirectional velocity, we have to have -1, just like Mina, you go to Mina and the image go out. So yes, sometimes we have to use some non-reflection boundary condition. Here is some job from Dr. Professor Torchado and Paul is used the same. We use the same similar formulas. Here is this for time match we use set or TVD arcade longer code method. Here is okay. Here I will show you our simulation result. This is one test case is right in thermal bubble. This is set order simulation result. We can see the produce the symmetrical structure perfectly. This is temperature, potential temperature, and horizontal ring and vertical ring. Here we use some dynamic dissipation field, a small dissipation field to remove some numerical noise. So this is fourth order scheme simulation result. The same is result we will get. We will perfect reproduce the thermal structures. Yes, here we show you our scheme, different resolutions, maximum potential, vertical velocity, vertical velocity. Here is speed and velocity, almost the same. I think our result is agree well with the other existing study like Adam Limden 2007 and Norman 2011. Yes, this is another testing test. Shows this set order scheme simulation result after 900 seconds. Is fourth order scheme. We can get yes some. We can get the potential perfectly. I think it's perfect. Yes, this is we use the different resolution to show how our scheme in convergence numerical solutions. This is MC4, 3, 4. We can see for high order, in fact, he convergent to the numerical solution very quickly. Yes, you can see quickly convergence to the numerical solutions. Maybe here is more clear. You can see third order, yes, or maybe on these resolutions is some oscillation, but for fourth order, he quickly to convergence solutions. Here I'll give some tables that's front locations compared with spectral element and DG method. Here we almost get the same simulation result. It is agree well with the other high order numerical methods such as spectral element and the discontinuous method. Yeah, this is internal gravity wave test. Is after 3,000 second simulation result. This third order scheme, this fourth order scheme. We can see high order scheme can better capture the detail like this. Very symmetry. But for fourth order, it is lost here. And yes, this is along the 5 kilometers. The different resolution simulation is all the profile. So it's quite similar to those for example, Skamalogan Camp, and in 1994, and Professor Giordo, and other exist studies like this. Next, I will show you the mounting test. This is current mounting profile here. This is our, we just show the part of the mesh domains. This mounting this. Yes, this is set all simulation result after 10 hours. Just port show you 2 hours result, yes. And the blue solid line shows our simulation result, and the red one shows the analytic solutions. You can see our simulation result very agree well with the analytic solutions. This is horizontal wing, and this is vertical wings. Yes, this fourth order scheme simulation result, very similar. Yes, we also calculate some root mean square errors compared to the analytic solutions. Here it shows our simulation result. So we compare to spectral element and the DG method. So we found in this test case, our root mean square is smaller than DG and the spectral element. We owe the part of reason to the boundary condition and the transformation we used the vertical coordinate maybe. So here I want to thank Professor give us the semi-analytic solution and the Scotty Mountain. Yes, summary. So here we present the two-dimensional compressible atmospheric core using third and fourth order multi-moment constraint finite volume method. In fact, in our method, it is different from the conventional finite volume because our predicted variable that is unknowns in our system is co-location within each cell. It is just a point value, just a volume. No included, no quadrature and something else, and also numerical conservation is okay, no problem. And another is no numerical quadrature in explicit involved in our schemes. And another important feature may be made our schemes more attractive as the accurate and practical numerical flow for atmospheric and oceanic modeling. One is just our predicted variable is node value at the solution point. It is, as I mentioned before, this solution point is very flexible, located within a mesh cell. And in this study, we used the equidistant solution point. In fact, also we have tried use the Gauss point or Gauss-Lyapunov point. It's not. I think it's very less sensitive low in our in our point solution point, but the constraint condition is very important. Yes, it's very convenient to deal with the complex geometry and the substance. On the other hand, high order and physical consistent formulation can be built by choosing a proper constraint in terms of not only numerical accuracy and efficiency, but also the underlying physics. Okay. In future, I will extend this job to 3 dimensions dynamic core. Use some popular spherical grid like cubic grid, yin-yang grid, and orthogonal geodesic grid and triangular geodesic grid. fact, this is shows some simulation result of your chiller water over the 4 degrees. It's cubic grid simulation. Lost space Howitz wave after 14 days. Cubic grid, young grid, and hexagonal geodesic grid and triangular geodesic grid simulation result. Okay, this is some reference. Thank you.
We have time for questions. Ram?
For the fourth order, how many Riemann solvers you are using for one element or one cell?
Riemann solver.
Yeah, how many?
Okay, I show. I mean, it's Riemann solver, right? We solve Riemann solver just on the interface. If we have, I mean, in one dimension, I mean,
One dimension is trivial. Two dimensions.
how many? We solve Riemann solver just on the interface, right? One cell, we have to compute this one, one element just have to have computed 2 times. So how many cells are just times 2? I think.
Anything else? Okay, let's thank our speaker one more time.